to record. All right, so what we talked about last time was moment maps and Hamiltonian group actions. And one of the main reasons that this is a notion people think is really important is you can use it to do this thing called symplectic reduction. I realized I skipped a little bit of context here. That's interesting. Okay. So I want to just add a little discussion, which is, so we talked about, I talked about a situation where I have a symplectic manifold and I have a symplectic Lie group action. So something I very, very often want to do with a group action is to mod out by it, right? From the perspective of physics, this is sort of, thinking about configurations that are related by some symmetry as the same. So I'd like to take this Lie group action, mod out by it, and get, well, natural kind of question is then, well, what do I get? What's the result? Well, whatever it is, it's definitely not symplectic, right? Because, there's no reason it should even be even dimensional. But I'm going to completely mess up the symplectic form, right? There's just no obvious way to take a symplectic form upstairs and turn it into any kind of reasonable structure in the quotient. That's a little bit of a lie, because if I think about my symplectic form differently, that becomes a bit more natural. In fact, if I have a reasonable quotient, so one of the issues where I'm going to have to hem and haw a little bit today is, if you take a manifold and mod out by a group action, there's no reason the quotient has to be a manifold. It could be some much more horrible thing. But somehow there are statements we can make about it which are kind of true if the result is a manifold, and kind of morally true in some more complicated sense if the result is not a manifold. And one of these statements is that it will be Poisson. I just push forward the Poisson bivector. So this is one of the good things about bivectors instead of two forms. Two forms I pull back, but very rarely does that give me something symplectic. Two forms I can push forward. And I still have to worry about getting a well-defined bivector downstairs. That's going to happen because the original bivector was invariant under the group action, because the original group action was symplectic. So, it's not so bad. I get something Poisson downstairs, something I can kind of put in this world of symplectic geometry, but it's essentially never going to be symplectic. Oops. So a natural question might be, well, what about its symplectic leaves? Maybe it has some natural symplectic leaves that are something we can understand. And symplectic reduction is essentially about how to answer that question properly. how to answer what the symplectic leaves of this guy are, how can we sort of, well, maybe we're not going to get the whole quotient, but pick out some good symplectic piece of it. All right. So that's kind of general table setting. Are there any questions about that? That's just kind of big picture. And now let's get down to brass tacks and talk about how this is actually going to work. So let me first kind of make a really basic observation. This has happened so many times now in this course where you have to kind of say, okay, let me first think about what happens with the linear algebra of symplectic vector spaces. And then I will be able to take some linear algebraic observation and have it descend down to something interesting. Well, not descend, be able to kind of patch it together at a bunch of different points on a manifold and get some interesting geometric statement. So in this case, the linear algebra statement I need is not going to obviously have anything to do with group actions. The rough idea is, so let me start with a symplectic vector space, as usual. You know, these often come up for us as tangent spaces to symplectic manifolds. But I'm just thinking about kind of an abstract symplectic vector space. And as we've discussed, there are sort of different kinds of subspaces of this guy. There are symplectic ones, there are Lagrangian ones. I'm going to look at the particular example of being co-isotropic. So being co-isotropic means that your symplectic orthogonal, this is the symplectic orthogonal, lies inside the subspace. So this is sort of something bigger than a Lagrangian subspace. Actually, one definition of being co-isotropic is that you contain a Lagrangian subspace, because the subspace contains Lagrangian and the symplectic orthogonal is contained in Lagrangian. All right. So in this case, we can restrict the symplectic form, thought of as a bilinear form. So this is one of these things you always have to keep straight when you're talking about a symplectic vector space, is there's sort of the kind of totally local thing. So I'm not talking about a symplectic form in the differential geometry sense. I really mean the bilinear map. I can just restrict that bilinear map to my subspace W, and it's still antisymmetric, and it's still bilinear, but of course it's degenerate. It will always be degenerate because the space W perp is exactly the radical, or Canis de Silva also uses the term kernel of this form. So fun observation, that means that if I mod out, so if I have any bilinear form, symmetric or antisymmetric, and I mod out by its radical, I get a non-degenerate form induced on the quotient. So I get an induced symplectic form on the quotient of W by the symplectic orthogonal. All right, so this is a sort of simple linear algebra observation, but it's going to be key for us moving forward. And the reason is that taking a quotient by a group action has the effect on tangent space of killing some of the tangent directions, right? And basically, when you take a quotient by a Lie group, you're saying that any tangent vector to the orbit through your point is getting smashed out of existence. The problem we're going to have with trying to make a symplectic form descend to the quotient is, well, like you don't even have a well-defined operation if you just mod out by a subspace. But if you instead take a coisotropic subspace and mod out by its symplectic orthogonal, you do get a well-defined symplectic form. All right. So now let's think about what this tells us about manifolds. So fix a symplectic manifold, M omega, and fix a coisotropic submanifold. So a coisotropic submanifold is one where, by definition, at any point in the submanifold, the tangent space to the submanifold to X is a coisotropic subspace of the tangent space to M, which is symplectic. All right, so now I can take my 2 form on M, I can pull it back to X. And what that means is exactly at each point of X, I restrict the 2 form to the tangent space of X. So I'm taking my symplectic form. In each tangent space, I'm restricting it to a coisotropic subspace. So again, this gives me something which is antisymmetric, still a 2 form, but it's not non-degenerate anymore. It has a radical at each point in X, which is given by the symplectic orthogonal to the subspace of the tangent space of X. And I'll call this N of X. So these subspaces define what's called a distribution on X. So they define at each point in X, I have some distinguished subspace of the tangent space, a direction I can go. Let me note, this is going to be a little bit of a mess, but I don't know why my iPad is being so slow today about this stuff. Sorry about that. So note the dimension of nx is equal to the codimension of x in my symplectic manifold. So it's equal to the dimension of m minus the dimension of x, because this is the property that symplectic orthogonal has. The symplectic orthogonal of any subspace in a symplectic vector space has dimension equal to the codimension of the original vector space, because it's isomorphic to the perp in the dual space. All right, so let me just, I think I have roughly this picture lower down, but let me kind of draw the picture you should have. So you have your whole manifold M here. I have, actually, this is hard to draw because I need, I need at least 4 dimensions to actually have a good example of this, but let me cheat a little bit and draw my whole manifold M as being 3-dimensional, right? And then inside there, I can draw X as a 2-manifold. I'm really lying. I should be at least drawing a 4-manifold with a 3-manifold inside it, but that's pretty hard to do in one note, so I'm not going to try. And at each point, so in this case, it's codimension 1. So what I'm going to get is at each point, I'm going to get a distinguished line, which is the stuff tangent to X, which is perp under this form to all the line where the restricted 2 form vanishes. So at each point in X, I'm going to have a distinguished line, which, I'm drawing as a tangent vector here, but I'm not getting any particular tangent vector in that line. I'm just getting the whole line in the tangent space. All right. So this defines what's called a distribution. That just means a field of subspaces of the tangent space with constant dimension. And this distribution, you can check, has a natural property, which is if I look at vector field, so a property of vector field on X may or may not have, is that at every point, its vector lies in this subspace N. That would be a section of the bundle N, thought of as a subbundle of the tangent bundle. And a property this may or may not have is that those sections might be closed undertaking Lie bracket. So this is a property that sort of is something about how the spaces nearby to each other relate. It's a little hard to, sort of explain geometrically what it means, but it has an important consequence we'll see in a moment. And you can check this by another one of these standard Cartan's magic formula calculations, that when I contract the symplectic form against a Lie bracket, there's a formula for that, which I think we used. Oh, I remember going through that formula. I don't remember what we were actually trying to do when we went through it. So, but I can take this I guess this was maybe when we were checking that the Lie bracket of two Hamiltonian vector fields is the Hamiltonian vector field associated to their Poisson bracket. I think that was the calculation we were doing. That if I take the Poisson bracket of two vector fields, which both lie in the subbundle N, I can check whether or not that is an N by contracting it with the symplectic form and seeing if I get 0. So I'll get 0 after contracting with the symplectic form, if and only if I'm a section of this subbundle N. And I can rewrite that contraction with the Lie bracket using this formula we proved when we were talking about Poisson brackets. I can then use Cartan's magic formula, and I can see that since the 2 form is closed and X and Y both have contraction with it, which is 0, that's enough to show that this contraction of the bracket with it is 0. So the 2 form being closed rides again. It always plays this really key role with the Lie brackets working out in the correct way. So the geometric significance of this fact is that locally, N is the tangent space to a foliation of your manifold by submanifolds. So there's a way of defining at least like a small bit of a submanifold through each point, such that they kind of all fit together and fill up an open neighborhood around that point, such that N is the tangent space to that submanifold. And this is one of these things that I'm not saying as carefully as I should, maybe, right? Because it's trivial to say that at one point X, N is tangent to a submanifold. That's easy. The non-trivial part is on an open subset, I can choose a sort of way of breaking that open subset up into submanifolds such that at every point in the open subset, it always has tangent space N. Right? So this thing about, you'll see if you like read about this, you'll see people call this an involutive distribution. To a section, I said integrable, which is really this geometric property. There's no local obstruction to it being the tangent spaces to a foliation. There might still be global issues. There's no guarantee that you can actually close these guys up into submanifolds. So kind of classic example of this. I don't think this actually comes from this coisotropic picture, but the kind of picture you should have in mind for what I mean when I say they might not close up is I can take the torus, and for any slope, I have a distribution given by, I'm thinking of the torus as taking the plane and gluing the sides. And so if I choose any slope, I can think of that as a distribution on the torus of one-dimensional subspaces, all the lines that have that slope. But if I take irrational slope, then well, locally at every point on the torus, it's totally fine. I have a nice foliation. But if I try to extend this guy to a sort of global submanifold that never closes up and it fills up the whole torus. So there's sort of no problem locally. There's no difference in the local geometry depending on whether the slope is rational or irrational. But if the slope is rational, your leaves are going to close up into nice closed submanifolds. And if your slope is irrational, they never will. And every one of them will be dense and there will be a huge mess. All right, so this is the kind of thing we have to worry about. But we can at least hope that we actually get a foliation by nice closed submanifolds. And again, this is kind of the picture. Now, before I had little tangent lines, and now I have actual one manifolds, more generally higher dimensional manifolds. Somehow this integrability thing isn't an issue for one-dimensional distributions. It's only for higher dimensional ones. All right. And I'm just again putting here this warning that I really would want to draw M being four-dimensional, in which case I'd have a three-dimensional coisotropic submanifold, and I could have a one-dimensional distribution. And I'll say here, I've seen a few different bits of terminology around this, but this is called the null foliation. Clearly, it should be called the null distribution, but I've never actually seen that anywhere. So the foliation given by restricting a symplectic form to a coisotropic manifold, and then looking at the kernels of the symplectic form as the tangent spaces to a foliation. All right, so what does our observation about linear algebra tell us? It tells us that X is not symplectic, but there is a symplectic form on something. It's on the normal directions to this null foliation in the in X. So somehow the space the symplectic form lives on, right, would be kind of these transverse directions to the null foliation in X. And now you see where I'm really getting in trouble with the dimensions, that those transverse directions, that should be two-dimensional, not one-dimensional. So what I wish I could say, what it would be nice to say is, well, I should be able to kind of mod out. There should be a manifold whose points are the leaves in the null foliation, and that manifold should be symplectic. Right? Should be able to kind of squash every pink line here, not pink, purple, and get a manifold where the tangent space is just given by these transverse directions, and I know how to define a symplectic form on those. I think I'm going to skip this part because I think there were actually a few lies in it. The kind of operative point here is imagine. So you should imagine that it could be possible that you would be able to take this quotient and then you would find, again, this is sort of warning, this is imaginary. This is not something you can always do. You would hope that sort of around each point, you could sort of choose coordinates where a certain number of coordinates are going along the leaf, a certain number of coordinates are going along the transverse space to the leaf. Leaf is what I call the submanifolds that are tangent to M. And you should be able to use those transverse coordinates to define a manifold structure on the space of the leaves. That doesn't always work. So somehow the way this is stated probably makes this sound a lot easier than it really is, but that's kind of the idea. I think we'll see why this kind of doesn't work. So kind of the picture you would like to have is that you have some space of leaves Y. And so I have X sitting as a subspace inside M, as a submanifold. I have it projecting down to Y by a submersion. And Y should carry a symplectic form that pulls back to, well, not the symplectic form on X, but the same thing as the pullback of the symplectic form on M to X. And if this happened, if kind of all of these maps actually existed and were well defined, you could check that this omega sub Y was symplectic, and life would be great. All right, are there any questions? So, somehow like a surprising amount of this is stuff about general coisotropic submanifolds. But I actually have one particular example of coisotropic submanifolds. Because we actually do have a large supply of coisotropic submanifolds, even if you don't happen to know about them yet, which come from Hamiltonian G actions on a symplectic space. All right, so yeah, I'm assume that I have some symplectic manifold, assume it has a Hamiltonian G action of a group. I'm going to find it very useful to have this terminology of regular values. So if I have a map between from a manifold to another manifold, I think I actually didn't put this definition down. Let me just write this kind of abstractly. I have a manifold M mapping to a manifold N by F. M and M is a regular point. Of this map. If the derivative TF from the tangent space at M of M to TF of N is surjective, and an element of N is a regular value, if every point in the pre-image of N is regular. So if all M in F inverse of N are regular. So this is one of these kind of standard things you have to be careful about. Are you thinking locally on M, or are you thinking locally on N? So being a regular point is something about how that map behaves on a little neighborhood around you in M, whereas being a regular value is about something that's happening on the whole pre-image. All right, and this is just relevant. It's with the moment map, one of the things we'll want to look at is which points in G dual are regular values of the moment map. And I'm just rewriting here the definition of being a regular value, that the derivative is surjective at every pre-image. And the reason that this sort of notion is very useful is because we know the implicit function theorem. And the implicit function theorem stated, not usually how you hear it, but this is essentially a statement of it, is that if I have a regular value, if I have a regular point of a map, let me actually write this again. Implicit function theorem. I think sort of the usual way this is stated, you can say if M is a regular value, then there exists a neighborhood U containing M such that if I look at the pre-image of the image of M and intersect that with U, then that is a submanifold.
Sorry, Ben, I'm totally confused.
Mm-hmm.
You started, sorry, your letter there is an N or is it an M? And it's in capital M or in capital N?
Oh, I'm sorry. I shouldn't. Yeah, I messed this up. I should have said regular point.
Okay, super.
Now, of course, if you have a regular value, you can apply this theorem at every point in the pre-image. So a consequence of this is if n in n is a regular value, then f inverse of n is a submanifold. And I mean, the proof of this top part, that's like somewhat difficult analysis, right? Basically, you say, oh, this is a local question, so I might as well just assume that my manifold M is Rn, right? I can replace M by any small neighborhood around M, so I might as well assume it's in Rn, and you get the statement of the implicit function theorem that you would find in an analysis course. And then this second implication is just, well, if n is a regular value, checking that the pre-image is a submanifold is a local question about each point in that pre-image, and well, that's a regular point. So the pre-image looks like a manifold at each one of those points. Okay. Before I start talking about the proof. Well, actually, before I start talking about the theorem. Okay, thanks for pointing that out here. So theorem if 0 is a regular point of the moment map, then its preimage is a coisotropic submanifold, right? So I kind of left submanifold a bit implicit here. The coisotropic submanifold. And of course, I actually only need the regular hypothesis so I can say submanifold. If it's not a regular point, then the preimage might not be a submanifold. And whatever it is, it's still trying to be coisotropic. The coisotropic part doesn't care about that, but it's not a submanifold, so it's kind of hard to talk about, hard to know what word to use for it. But it'll still be coisotropic at any regular point, even though it might have some weird singularities. All right, so this theorem, this is one of these theorems that it's not hard, but you have to think carefully about all the definitions in the picture. So how do I think about the derivative of the moment map? Well, it's almost, what I would like to say is that I look at the map from the Lie algebra into the tangent space, which I get by differentiating the action, and I dualize that. Right? So that gives me a map to G dual, that's good, but it gives me a map from the cotangent space to G dual, not from the tangent space. So I have to also use the map a tangent vector contracts with the symplectic form to go from the tangent space to the cotangent space, and then use the dual of that. All right. And this is just restating the moment map condition. Oops. Right. The moment map condition is if I take the differential of the function mu x, then that's equal to the contraction of the vector field xm with the symplectic form. So what I'm saying here about the derivative is kind of restating this, where instead of taking the differential of the moment map after I contract it with a tangent vector, I instead think about dualizing the map from the, anyways. So this is just sort of a little bit of playing with linear algebra to go from this equation to this statement. So what that tells me is that the kernel of this, the differential of the moment map, the derivative of the moment map, is the symplectic orthogonal to the tangent space to the G orbit through the point, right? So the way to think about the image of this map from the Lie algebra to the tangent space is I'm taking the derivative of the map, act on my point with an element of the group. So I'm getting the tangent space to the G orbit through that point. The picture you should have here is that here I have my group, here I have the orbit through the point G. So I have a map here that sends G to G acting on P. And then this orbit includes into M in the obvious way. Right, so this map is also G maps to G times P. And if I take the tangent space at the identity here, which maps to P here, which maps to P here, I get the Lie algebra acting surjectively to the tangent space of this orbit, and then including in the obvious way to the tangent space of M. All right, so the kernel of the derivative of the moment map is the perp to this tangent space. All right, great. On the other hand, because mu is equivariant for the usual action on M and the adjoint action on the tangent space, on the dual of the Lie algebra, that means that mu inverse of 0 is invariant under the action of the group. So this whole orbit, should have written this slightly differently, this whole orbit actually sits inside mu inverse of 0, which sits inside M. So that means that the dual to the tangent space sits inside the tangent space to mu inverse of 0, sitting inside. All right. And I'm cheating a little bit here. This was maybe a bad thing to write, because I shouldn't have written this here. That was bad because I don't know yet that mu inverse of 0. I haven't used that it's a manifold yet, so it's kind of bad to write that. What's maybe better to think about is if I have some path inside the group, right, given any element of the Lie algebra, I can create a path from R into G such that the derivative at 0 is my chosen tangent vector. And it's sometimes useful to think about pushing forward tangent vectors this way. So, right, I can think about this map as, well, now I act on P. I consider the path gamma of T acting on P. And then if I hit that with the moment map, well, like I said, the moment map is equivariant. So if mu of P is 0, then mu applied to this guy is always 0, right? And so this implies that that G is mapping into the kernel of the derivative of the moment map. Right? Because ultimately, what does it mean to push forward a tangent vector? It means to think of it as the velocity vector of some path, compose that path with your map, and see what velocity vector you get on the other side. And we see here, oh, we always get the velocity vector 0, so that means I'm in the kernel of this derivative. Okay. So that was showing this result, that the tangent space to the orbit is contained inside the kernel of the derivative to the moment map. Okay, so what does this tell us? This tells us that this subspace is isotropic. It's contained in its symplectic orthogonal, right? We already saw that this guy is the symplectic orthogonal to the tangent space to the orbit. And so the kernel of this derivative of the moment map is co-isotropic. Okay. And as I say, it's just worth noting, all of these calculations have not used anything about regular values yet, because I've expressed everything in terms of the derivative of the moment map. I haven't said anything about what the level set is. Now, If P is a regular point, so this derivative is surjective, then by the implicit function theorem, as I said above, near that point P, mu inverse of 0 is a submanifold. So it might have some singularity somewhere else, but near that point, it's a submanifold. And of course, if I have a regular value, then at every point in the preimage, I get to use that argument. And I always look like a submanifold, which is to say, I am a submanifold. So as long as 0 is a regular value, I get that mu inverse of 0 is a smooth submanifold. Its dimension is the dimension you would expect. It's the dimension of M minus the dimension of G, because I'm mapping to the dual of the Lie algebra, which has same dimension as the group. And the tangent space to that submanifold is actually the kernel of the map. Right? Exactly what happens at irregular points, points which aren't regular, is the dimension of the kernel jumps because the map stops being surjective, but the level set doesn't become a submanifold with that bigger dimensional tangent space. It just kind of, have some funny singularity where kind of if you took all the tangent vectors to all the paths through it, you would get that big space, but you don't get a submanifold. If you're used to thinking about algebraic varieties, it's like a singular point of an algebraic variety, right? There's an algebraic version of the implicit function theorem, which says essentially the same thing, where instead of submanifold, you say is a smooth point of the level set. All right. So one of the reasons that I'm kind of emphasizing that I'm using some theorem to interpret the kernel of this derivative as the tangent space to something is we already know the right-hand side is coisotropic. Thus, this moment map level is coisotropic as well. Yeah, and as I say, if P is not regular, then somehow morally it's still trying to be coisotropic, but what that means is something a lot more complicated. All right, I guess I repeated myself, but that's fine. All right, are there any questions about this proof? Okay, then let's take a quick pause, and I will be back in a moment to resume recording. All right, so I discussed before, coisotropic submanifolds have this natural foliation, null foliation. And we actually figured out exactly what that is in the course of the proof, right? We're supposed to be looking at the perp to the tangent space of the coisotropic submanifold. That's the tangent space to the G orbits, right? So the leaves of the null foliation are exactly the G orbits. So, right, another sort of way of saying this is what you had asked about. When is the moment map preimage one orbit? Well, you would need the symplectic form to vanish when you restricted it to that orbit, which again, by sort of for dimension reasons, is going to happen exactly when the dimension of the group is half the dimension of the symplectic manifold. All right. And one of the things about regularity is actually going to, so let me just note here, oops. Being a regular point of mu is true if and only if the Lie algebra of G mapping into the tangent space there is injective. Right, the dual of a map is injective if and only if the original map is surjective. So essentially, regularity tells us that the orbits have to be submanifolds whose dimension is the same as that of the group. And it's really, really tempting to say that means that the action of the group is free on the moment map level, right? That the stabilizer of each point is trivial, but that's not right. What it shows is that the stabilizer has trivial Lie algebra. And as long as our action is reasonable, the stabilizer is going to be closed and thus a Lie group. So having trivial Lie algebra means that it's zero dimensional. So it must be discrete, but it might be non-trivial. So that's just something we're going to have to watch out for. That you'll sometimes hear this called locally free. So being a regular value of the moment map means that there must be some neighborhood of the identity with no element of the stabilizer in it. So that's the sense in which it's locally free, but there might be elements of the stabilizer somewhere far away where the Lie algebra can't see them. So it's annoying, but say la vie. All right, well, in this case, I had said like, oh, wouldn't it be nice if there were some reasonable space where the elements were the leaves of the foliation on the coisotropic submanifold? And, so in this case, what I'm asking for is a quotient by the action of the group, right? The leaves are the group orbits. So a space whose points are the leaves are the space whose points are the group orbits, the quotient. Now, it is a complicated issue, and one can go kind of deeper and deeper on of kind of in what circumstances does this quotient make sense? Exactly how bad can you let the action be and have some kind of reasonable interpretation of what this quotient is. But there's also sort of a reasonable set of hypotheses we can add, which will make the quotient a manifold. So if the group is compact, I can actually loosen this and ask that the group action be proper, but let's just say the group is compact, saves us some trouble. And its action on the moment map preimage is free. So that's a stronger condition than zero being a regular value. I'm really requiring that the action be free. Then this reduced space, M red, so that's the moment map level mod the action of the group, is a manifold. Its tangent space is given by, the tangent space to the moment map level, mod the tangent space to the orbit through each point. And that's a coisotropic submanifold mod its symplectic orthogonal, right? So this is TP mu inverse of 0, which is coisotropic mod the orthogonal space to that. Okay. So that form, which gives me a 2 form on this reduced space, and that's a symplectic form. So this makes this reduction into a symplectic manifold whose dimension is the dimension of M minus twice the dimension of G. And the reason it's twice the dimension of G is, well, One of those dimensions of G comes from the fact that the moment map level is a submanifold with codimension dimension of G. And then when I mod out by the action of G, I lose the dimension of G again. And so I get dim M minus 2 times the dimension of G, which is convenient. G might be odd dimensional, but this keeps me always even dimensional, right? M must have been even dimensional because it was originally a symplectic manifold. So this reduced space had better be even dimensional again. And, I'll just note here, this is, again, a sort of standard linear algebra thing, right? That going from a co-isotropic subspace to this quotient, right? I lose the codimension of the co-isotropic subspace once by restricting to the subspace, and then I lose it again by modding it. All right. So I can, out of this moment map level, make a new symplectic manifold, but I have to both do the operation of restrict the moment map level and mod out. And if I only do one of those on its own, I won't get something symplectic. When I restrict the moment map level, I get something co-isotropic. If I just mod out, I get something Poisson. And then this reduced space is where they meet. All right. Any questions about this statement? So we sort of have all the pieces to think about this, but let me just kind of go through it. So again, since G is acting freely, I didn't need to separately assume that 0 is a regular value. That's automatic. Because at each point, the Lie algebra injects into the tangent space, and so dualizing the derivative of the moment map is surjective. All right, so I have a regular value. This moment map level is thus a submanifold. And so I'm acting on a manifold with a compact group, and it's a free action. So there's a general theorem that when I do that, the quotient is a manifold, and it has the obvious tangent space you would expect, that you take the tangent space of your original guy and mod out by the tangent space to the orbit. Okay, so this tells me that M-red is a manifold. And really all of these hypotheses I need for M-red to be a manifold. If I have some weaker hypotheses, and M-red is something else. So for example, if I only assume that I have a regular value, then this reduced space, it won't necessarily be a manifold, it could be an orbifold. And there's a notion of symplectic orbifold, and it's sort of easy to check that this guy is going to be a symplectic orbifold. So somehow, whatever you get, it's symplectic, but it might be something weaker than a manifold. All right. So M-red is a manifold. I just have to show it's a symplectic manifold. So how do I actually kind of cook up this symplectic structure? Well, when I take my original symplectic form and I restrict it to the coisotropic submanifold, it's still a 2 form, but it's not non-degenerate anymore. However, precisely because it vanishes on the tangent space to the orbits, it descends to a 2 form on this quotient space, right? I can compute it as a 2 form on the tangent space downstairs by saying, take any 2 vectors here, look at any pre-images, apply the form to those upstairs, and I get an answer that doesn't depend on which pre-images I chose. So exactly because the tangent space to the orbit is the radical, I get an induced non-degenerate form on the quotient by the radical. All right. So in fact, there's some 2 form omega red downstairs whose pullback is the restriction of omega to the moment map level, and that's a symplectic form. And I'll just note here, how do I, well, I take the exterior derivative of omega red, pull back, commutes with exterior derivative, so that's the same as restricting omega to, should have put the moment map level here, to the moment map level and taking d of that, which is 0 because it's the pullback of d of omega on the whole ambient space again. And precisely by this kind of descent argument, checking that d of the pullback of omega red is 0 implies that d of omega red is 0 because I have a submersion, right? So if I want to compute d of omega red on any 3 vectors, I can pull those back to the moment map level and apply d of omega upstairs to those. And well, I always get 0, so I'm going to get 0 downstairs as well. So this shows that m red and omega red give me a symplectic map. All right, any questions?
Sorry, I blanked on something a little earlier. Could you just quickly remind me again why the orbits to a why the tangent space to the orbits are isotropic for a group action? G.
Because they're the perp of a coisotropic space, right? So the perp to the tangent space to the orbit is the tangent space to mu inverse of 0. Right? Taking symplectic orthogonal is an involution. So proving that the symplectic orthogonal of the tangent space to the moment map level is the tangent space to the orbit is the same as proving that the tangent space to the orbit has symplectic orthogonal given by the tangent space to the moment map level. So, you know, somehow the point here is exactly that when you mod out by the action of the group, you lose some tangent vectors. And you have to pull back to the moment map level to throw out an exactly compensating set of tangent vectors on the other side. And that's essentially what the fact that these guys are symplectic orthogonal to each other proves. That the tangent space to the moment map level is symplectic orthogonal to the tangent space to the G orbit.
Thanks.
So, you know, ultimately the proof of that is up here. Okay. Great. Oops. Blew right past all my examples. Okay. So I've got a bit of time left. Let's actually think about some examples, find out something about how this behaves. But before I can talk about any interesting examples, let me make a note. It might seem a little strange that we only use 0, but I'll note here, it was actually really key that 0 was preserved under the coadjoint action. So I genuinely could not go through the whole same argument if I picked just any element of G dual. But if I pick an element of G dual that's invariant under the coadjoint action, I know this got a little messed up. Let me just delete this. So if I take any element of G dual, which is invariant under the coadjoint action, then I can just run through the same argument. And its moment map level will be invariant under G. You can mod out by it. I'll just note that doesn't actually get us any extra generality, because if I take any element invariant under the coadjoint action, I can subtract that off globally from the moment map and get a new moment map. So I can think of that as, oh, actually, no, I didn't reduce at a different point. I changed my moment map. And probably different ways, like usually actually I think of having one fixed moment map and reducing at different points, but that's completely equivalent to choosing different moment maps and always reducing at 0. maybe one thing I'll mention, sort of debated when to insert this because it's a little bit random. You might ask, what if lambda is not in the invariance under the adjoint action? And the answer then is you get something genuinely different. You really have to do something else. What you can do is consider the moment map, the coadjoint orbit for lambda, the whole coadjoint orbit. You can take mu inverse of that. And then, well, you haven't kind of lost as many dimensions on top. So you can only mod out not by all of G, but by the stabilizer of lambda under the coadjoint action of G. So you're both losing fewer dimensions when you take the moment map preimage, since you're taking a preimage of an actual submanifold, and that's exactly compensated for by you mod out by smaller group. All right, so that's just how life is. For non-abelian groups, life is more difficult. That's just the way the world is. All right. So let's, as I say, let's do a few examples. Maybe one of the more interesting ones is I have Cn, which I think of as a Kähler manifold. So I have the usual Hermitian inner product on Cn. I think of the real part of that as my Kähler metric. Think of the imaginary part of that, which is actually anti-symmetric, as the symplectic form. And as usual, I can kind of rewrite that as dxk, which dyk. So I have an action on here of scalar multiplication by unit complex numbers. So this is an action of S1, which I think of as the real numbers mod pi times 2 pi times the integers. All right. So if I look at the derivative of this S1 action, so the Lie algebra is one-dimensional and isomorphic to R. Looking at the derivative with respect to this, I get the vector field x1 ddyi, xi ddyi minus yi ddxi. So this is the vector field for clockwise, counterclockwise rotation in the xi yi plane. And I take the sum of all of these because I'm doing that rotation in each one of those planes. When I contract that with the symplectic form, I get minus xi dxi plus yi dyi. And so taking the antiderivative, this is the exterior derivative of minus 1/2 x squared plus y squared, summed over all i's. And if I think about what that means I'm taking the function minus 1/2 norm squared. And I'm taking d of that. So this guy is the Hamiltonian function for my S1 action. All right, so I can think of minus 1/2 z squared, norm squared, plus any constant I want. And as I said, I'm going to stick with always reducing at 0. So the way to get different reductions is to shift my moment map, right? In this case, adding constants to it. So this is a moment map. What happens? if I take, oops, sorry, I think I had a small error there. If C is positive, then I'm looking at things with a particular fixed norm. I think oh, whoops, no, I still have 2 still isn't in the right place. It's things of norm 2c square root 2c. So it's a copy of the 2n-1 sphere with some fixed radius. And the radius is going to be relevant because I'll get a different symplectic form for different values of c. So even though all these levels are isomorphic, they're isomorphic by an isomorphism that's scalar multiplication. So it scales the symplectic form. The isomorphism between these is not going to send the restriction of the symplectic form to one, the restriction of the symplectic form to the other. Right. Now C, if C is positive, then it's a regular value of the moment map. You can check that the map sending an element of Cn to its norm squared is, its only critical point is 0. So here I'm asking is 2c critical point of that function, and it's not if C is positive. So it's a regular value, and the quotient by the action of S1 is Cpn-1, right? So what's happened here is every complex line intersects this 2n-1 sphere in a circle. And scalar multiplication by unit complex numbers acts transitively and freely on that circle, right? So what's happening here is every line has its own unit circle inside it, and that's its intersection with the unit sphere, or more generally, the sphere of radius square root of 2c. So the quotient space is Cpn-1, and okay, we have another proof that Cpn-1 is symplectic. And in fact, this does, up to scalar multiplication, give you the Fubini-Studi form, and you can even get the Kähler metric out of it as well. If C equals 0, then this is not a regular point, not a regular value. Value of mu, and well, not unrelatedly, I get a point where the circle acts trivially, right? I'm just getting the origin, and my group acts trivially. So you see how this sort of, the moment map stops being regular. Well, that exactly means that the vector field coming from the S1 action becomes 0. And so the S1 action has to be trivial. And if C is less than 0, then the preimage is just empty. And so, I mean, the theorem is correct, but it's boring. And this is actually sort of a reasonably common phenomenon that you might think, somehow any moment map should give you roughly the same symplectic reduction, but actually things can go very wrong. Somehow one way to say this is that when C is negative, there are sort of various expectations about the behavior of the symplectic reduction, where we would expect the symplectic reduction to have negative volume, for example. And well, that's just not possible. Whenever you get these nonsensical predictions, that probably means that the symplectic reduction is just empty. And an empty, the empty set is manifold, and it's even a symplectic manifold. So there's no contradiction with the theorem, but it's sort of a boring statement. All right. Any questions? So I want to talk about a sort of small modification of this, which I actually think, illustrates this issue about freeness. If we consider the S1 action on C2, where instead of acting by scalars, I act by, e to the 2I theta on one coordinate and e to the 3I theta on the other coordinate. So you can check that this is going to be a faithful action of S1, right? Choosing a generic point of C2, no element of S1 will have a non-zero stabilizer. So I have a moment map in this case. You can check that in order to go twice as fast, what you have to do is multiply the moment map by 2. Right? You're multiplying the corresponding Hamiltonian vector field by 2. So you're going twice as fast in the Z1 coordinate and 3 times as fast in the Z2 coordinate. And actually, I should just mention, with these moment maps, it's very rare that you actually kind of find one from scratch. There are kind of a few standard calculations that you usually are, applying some version of and then modifying a little bit to suit your purposes. So in particular, right, I can think of the N torus. So this is, Rn mod 2 pi z to the n acting on Cn. And of course, this is just n copies of S1, and each one of those copies of S1 is acting on one of the coordinates in Cn. So I can just take my theorem from before and apply it here in a straightforward way. And what it tells me is that the moment map, mu of Z1 up through Zn is equal to, each coordinate of it is minus 1/2 the norm squared of one of the coordinates. Right. So all I'm doing here is I'm then using the fact that I can think of this copy of S1 as a subgroup inside S1 times S1, and then using the usual rule for getting a moment map for the action of a subgroup. Okay. Just in case you're wondering where the hell I got this from. You can check that this is also regular at 0 as long as the constant I shift it by is not 0. And if C is positive, then I get a regular value, but there are 2 orbits that have non-trivial stabilizer. So almost all of the orbits are free. All the ones where both coordinates are non-zero. But then there are 2 orbits where one of the coordinates becomes 0, or the value of the other one is essentially fixed, up to multiplication by unit scalar. And those guys, one of them has stabilizer Z mod 2, and one of them has stabilizer Z mod 3, from the fact that now, pi, theta being pi, or 2/3 times pi, gives me a point in the stabilizer. So in this case, the quotient isn't smooth, it's an orbifold. So at most points, it looks like a manifold, but then near those orbits that have bigger stabilizers, it doesn't look like R2, it looks like R2 mod the action of this finite group Z mod 2 or Z mod 3. This is sometimes what's called a football orbifold because it has 2 points where something funny is happening, and it looks more kind of like some kind of cone. This is just to sort of illustrate why I have to actually say, like, it really is a genuine extra hypothesis that the action is free. And actually, this comes up a lot in these kind of toric examples, that you get these orbifold structures. All right, any questions? Okay, I'm almost out of time, but I want to do one non-abelian example. So consider the K by N complex matrices with UK acting by left multiplication. So this is a left action of the unitary group UK. This K by K matrices whose inverse is their transpose conjugate. You can check that the moment map in this case sends A to A times A conjugate, and I have to multiply by I over 2. And then I subtract some multiple of the identity matrix. And here I'm thinking of the Lie algebra of UN, and its dual is isomorphic to skew Hermitian matrices. And you should think of this as a generalization of this formula involving the square. That's the case of U1. And this A times A star, some generalization of that norm squared that was showing up before. And I won't sort of carefully check this again. I'll say this is sort of one of these things where you can decompose it into a simpler calculation. You only really need to check the case where N is equal to 1. Because this action really, like, right, UK is acting on each column separately. Yeah, each column. So it's, if you're only thinking of it as the UK space, it's just N copies of UK acting on C to the K. You do the calculation there and you're done. So just as before, when I took a square and I said, okay, C is going to have to be positive, here, this A times A transpose conjugate is positive semi-definite. So the moment map pre-image is empty if C is negative. It's a point if C is 0. A would have to be the 0 matrix. And if C is positive, then being in the 0 level of the moment map is actually saying that the rows of the matrix A are an orthogonal set of K vectors in Cn, whose length is the square root of 2C. And then I'm going to take such things, UK acts on those by taking linear combinations, and I mod out by that. And if you sort of think this through, what happens then is I'm only remembering the space they span. So any k-dimensional subspace of Cn has a basis like this that's orthogonal with this fixed length. So I want to say orthonormal, but it actually depends on C. And that UK acts freely and transitively on the set of those bases. This is basically thinking about A transpose as a map from CK into Cn, taking the image of that map. And then the unitary matrices act by pre-composition, so taking linear combinations of these guys. So when I do the symplectic reduction, what I get is the Grassmannian of K-planes in N space. So you can get lots of interesting spaces by doing this. This is sort of one of the cool examples. All right, let me pause or stop there. I'm after 2:30 and just ask if people have questions. All right, no problem. We'll come back to this next time.